Welcome back. This will be our second video lecture on section 3.7 of the text concerning applications of matrix algebra. In our first video lecture, we covered Markov chains and steady state, and in this second lecture, we'll cover population growth. Now let's consider the following example. A certain species of German beetle, the Vollmar-Wassermann beetle, lives for at most 3 years. Now we divide the female beetles into 3 age classes, 1 for each year. The youths from 0 to 1 years, the juveniles from 1 to 2 years, and the adults from 2 to 3 years. Now the youths do not lay eggs. Each juvenile produces an average of 4 female beetles, and each adult produces an average of 3 female beetles. The survival rate for youths is 50%, and the survival rate for juveniles is 25%. Now we can encode all of this information in a graph. So the vertices of our graphs are the youths, denoted by this Y, the juveniles denoted by J, and the adults, female beetles, denoted by A. And we can see, for example, that 50% of the youths will, in the next year, produce a juvenile beetle. 50% of the youths survive to become juveniles. And in the next generation, 25% of the juveniles will become adults. Now, the youths don't lay any eggs, but each juvenile produces on average 4 youths in the next generation, and each adult produces on average 3 youths in the next generation. So this graph tells us about how these different age groups within the population of the female beetles communicate with each other. Now let us suppose that at present there are 100 females, 50 youths, 30 juveniles, and 20 adults. We can store these in a population vector where row 1 tells us about the youths, row 2 the juveniles, and row 3 the adults. And we're going to label this vector x sub 0 because this tells us the state of the population at, let's say, time 0. Now we want to let x1, x2, x3, etc. be the population vectors after 1 year, 2 years, and 3 years have elapsed. And we want to study the evolution of this population of female beetles over time from one generation to the next. Now let's consider the following problem. First, show that xn plus 1, the population vector after n plus 1 generations, can be calculated from xn through matrix multiplication. So that is, there exists a 3 by 3 matrix L such that xn plus 1 can be calculated from xn by multiplication by this matrix L. Second, use matrix multiplication to find x1 through x5. And then finally, in part 3, for each population vector x1 through x5, determine the fraction of the population that is in each of the 3 age groups. So let's go to the document camera and work out parts 1, 2, and 3 of this problem. All right, welcome to the document camera. What we're going to try to do is describe the process by which we can use the end state population vector and produce the n plus 1 stage population vector through a matrix multiplication. So what I've got here is my nth vector, x sub n. I have generic entries y sub n, j sub n, and a sub n to denote the number of youths, juveniles, and adults in generation n. And here we have the same quantities now in generation n plus 1. So what we have to do is describe how we could generate these values from these values using matrix multiplication. All right, let's first think about this very simply, right? So how would I describe the number of youths in generation n plus 1? Well, the youths in generation n plus 1 come about through the laying of eggs by, in this case, only the juveniles and the adults. Since the youths don't lay any eggs, they cannot produce any youths in the next generation. So the youths in generation n plus 1 come about from the juveniles in generation n, and it's 4 for every juvenile in generation n, and it's 3 for every adult in generation n. So we could simply say that the number of youths in generation n plus 1 is going to be nothing times the number of youths it's going to be 4 times the number of juveniles, and it's going to be 3 times the number of adults in generation n. All right, now how about juveniles in generation n plus 1? Now, the only way to become a juvenile in generation n plus 1 is to have survived from a youth in generation n. And that happens, we get 50% of the youths in generation n will survive to become juveniles. And so this is simply going to be 0.5 times the number of youths in generation n. And then just to complete this, we could say nothing times the number of juveniles and nothing times the number of adults in generation n. And how do we become an adult in generation n plus 1? The only way to become an adult in generation n plus 1 is to survive as a juvenile from generation n. So there's a certain number of juveniles in generation n. 25% of them survive to become adults. So we'll get 0 times the number of youths, 0.25 times the number of juveniles, and 0 times the number of adults in generation n. Now, if we look at this, this is telling us that this vector with components yn plus 1, jn plus 1, and an plus 1 can be obtained by multiplying the matrix. We can see the coefficients here, 0, 4, 3, 0.5, 0, 0, 0.250 times the vector yn, jn, and an. In other words, these equations, these 3 equations that tell us how to get the youths, juveniles, and adults in generation n plus 1 can be thought of as this matrix multiplication. All right. So in short, we're seeing that xn plus 1, the nth plus first generation population vector, is simply just the product of this matrix, which we'll call L, times the vector at generation n. So xn plus 1 is just L times x sub n. Now, doing this kind of matrix multiplication is very easy for a machine, so we can easily take this input vector x1 and work through from x0 to x1 and from x1 to x2 on up to x5. And so I did that just to save us some time and just so you don't have to watch me, plug things in and crank them out using the machine. Let me just show you the results. So x0, that was our initial information here. That consists of 50, 30, and 20. That's x0. In the next generation, x1 is going to be 180, 25, and 7.5. So that's x0. This is x1. All right. x2, when I take this vector x1 and multiply it by L, I'm going to get x2. And x2 consists of 122.5, 90, and 6.25. That's x2. In the next generation, we'll have x3, and that consists of 378.75, 61.25, and 22.5. That's x3. x4 is going to be 312.5, 189.375, and 15.312. And I computed one more. Let's go all the way out to x5. For x5, we're up to 803.438, 156.250, and 47.344. Now, I think it's pretty clear by looking at the data, right, that the total number in the population here, the total number is only 100. Our population of females, at least, is of size 100. And by the time we've gone 5 generations into the future, we've got a population that's close to 1,000, right? So you can see that the population is growing. In fact, it's not hard to show using some math that this population is actually growing exponentially fast, all right? So as the successive generations ensue, we're going to see the total number of at least females in our population is going to be growing exponentially. Now, what is interesting to notice, though, right, is that these numbers are not going up directly, right? So we can see that the population of youths, right, is going from 50 to 180, down to 122, up to 378, down to 312, up to 803. So the youth population is seesawing. It's going up and down. We can see also in the juvenile population, it starts at 30, goes down to 25, goes up to 90, down to 61, up to 189, down to 156. So that population is also kind of seesawing up and down. And we can see exactly the same behavior in the adult population, because remember, these populations are communicating with each other. The youths are producing the juveniles are producing the adults, and the adults and the juveniles are influencing the youths. And so as this kind of cyclic behavior gets started, it will continue. All right, now, what we can do, though, and what is interesting to look at, even though the population is growing exponentially, it's interesting to kind of look at the fraction of the population in each generation that is composed of youth, juveniles, and adults. So what we can do is simply add up, in each case, add up the total number of the total weight of this vector. So we can add up the first, second, and third components to get the total projected population in, let's say, generation 2. We can take that total and divide it into each of these entries and get that proportion of the total that's in, let's say, the youth population, the juvenile population, and the adult population. So we can look at these kind of companion vectors. And when I did that for these 5 vectors, you can get the following kind of behavior for the proportions of youths, juveniles, and adults in each of these generations. So in the first generation, there's 100 total females. And so when I simply divide each of these by 100, it's very easy to see that this becomes 0.5, 0.3, and 0.2. When I do the same thing in generation 1, when I take the total and divide each of those by the total, we can see now that the youths compose 84% of the total, the juveniles 12% of the total, and the adults now only 4% of the total. Okay? When I go to generation 2, I see that the youths now only compose 56% of the population, the juveniles 41% of the population, and the adults only 3% of the population. So we're getting this surge in the juveniles in generation 2 because there were so many youths in generation 1. So that surge in juveniles is created because of this large proportion of youths in generation 1. Okay, going into generation 3, we can see that the proportions are 82%, so 0.82, 0.13, and 0.05. Okay, so only 5% of generation 3 is adults, 13% is juveniles, and 82% are youths. In generation 4, we can see that this is 60% composed of youths, 37% are juveniles, and 3% are adults. And then when we go to generation 5, the proportions of youths, juveniles, and adults is 80%, 16%, and 4%. Okay? Now, this is not work that's easily done by hand, and it's easy to kind of turn this work over to the computer. So let's go ahead and head back to the class notes and kind of observe this phenomenon using the computer to do these calculations for us and to do some graphing for us. So let's head back to the class notes and see what's happening to these proportions as n goes to infinity. Now, in our example, the population of female beetles is actually growing exponentially. But if we look at the proportion of the population that's in, let's say, the youth group, the juvenile group, and the adult group, they are actually achieving stability. Now, we can see this in the graph. I took the specific example that we were looking at, and I plotted the number of, or the proportion of beetles that are in the youth group, and they're shown in red, the proportion of the juvenile group shown in blue, and the proportion of the adult female beetle group, and they're shown in green. And just as we saw in our calculations, early on, the population of youths, the population of juveniles, and the population of adults, they're all oscillating. They're kind of going up and down for a few generations. But what this picture is revealing to us is that, say, after about 30 generations, and for sure after 40 generations, we see that these proportions, the proportion of the populations that's in the youth group, is really settling down at about 70%. So after about 30 or 40 generations, we're seeing about 70% of that beetle population is going to be in the youth group. About, let's say, 25% of the population will be in the juvenile group, and only about 5% of the population will be in the adult group. So even though the population itself is exploding exponentially, we do see that it stabilizes in terms of the proportion of the population that's in, let's say, the youth group, the juvenile group, and the adult group. Now, the example we worked fits into a larger class of examples where you might subdivide the population into 4 groups or 5 groups, or in general into n groups. Now, the matrix L from our previous example is typically called a Leslie matrix, and in general, a Leslie matrix would be a square matrix of this form. Now, the entries across this top row, the BIs, are generally called the birth parameters because they tell us how each of these successive groups will populate that lowest group. And the entries S sub I here just below the main diagonal are the survival parameters because they tell us how group 1 will survive to become members of group 2 and how group 2 will survive to become members of group 3, etc. So we've got the birth parameters across the top row and the survival parameters along that sub-diagonal. And in general, we'll find that we can take a population vector and find the population vector corresponding to the next generation through matrix multiplication. So the population vector at generation n+1 will simply be L times the population vector at x sub n. In other words, this will conform to what we saw in our previous example. All right, so I think you are now prepared to go off and do some examination of Leslie matrices and population growth on your own. And so this completes the second part of our lecture, part B, from section 3.7. I hope you've learned something both about Markov chains, but about population growth. And I encourage you to go off and work some problems and study this further. We'll see you again when we begin chapter 4. Until then, take care. Bye-bye.